YouTube.
Okay, no problem.
Within 2 minutes.
Yeah. Please share me the link also, YouTube link on WhatsApp,
Yeah, yeah.
so that I can open it in mobile.
Yeah, just shared you the link on the WhatsApp.
Okay, got it. So, so it's public now.
Yeah, it is public now.
Shall I start the that promotional video?
Yeah, did you share it with along with the audio, na?
Yeah, along with audio, I click that option.
Yes, yes. So, good morning, everyone. We are live now, and I would appreciate if you will be writing your name of the city and state where you live present. So, good morning, everyone. Please mention your name of the city and state from your life. So, Sushil Pandit is from Ahmednagar. Thank you very much. Amol Bansore from Narhe, Pune. Hariom Gupta is there. Welcome, Hariom Gupta. Sudhir Pange is there. Welcome, all of you. Write down your name of the city and state. So, mention the name of the city. And your state. So Nilesh Salunke is there from Maharashtra, Adarsh College of Pharmacy. Dr. Nilesh Salunke, sir, welcome. Sheetal Garg is also there. So welcome all of you. Ajit Jadhav from Maharashtra. So please write down the name of the city and the state. Dr. Anand Shetgar sir, welcome. Lakshman Padwe is there from Nanded. Rahul Sachdev is there from Rahul Sachdev is from Karad, Maharashtra. Vinayak is there from Maharashtra, Pune. So write down the name of the city and the state where are you live from. Indrajit is there from Mumbai. Sorry, Indranil Dhawale is there from Mumbai, Maharashtra. So write down your name of the city and state. So welcome to this great session of homology modeling. We are having a great speaker of Scott Engineer. He is a Scott Engineer application scientist. Dr. Horne is there from Tamil Nadu. Nikhil Pushpakar is there from Ideal Institute of Pharmacy, Palghar, Maharashtra. And it's very wonderful to see all of you on this great morning. So Smita is from Sangli. So write down the name of the city and state you are live from. Very shortly we'll be starting the session. So Gritika Kanojia is from Pune College of Pharmacy, Pune. Very nice. Tejaswani Bodke is from Nasik, Maharashtra. Welcome, Tejaswani. Welcome, welcome all of you. So share this information to all of your WhatsApp group. You can share the live link to all of the groups you are having so that the maximum student and teachers can be benefited from it. So this is how we are going to start the session in next 8 minutes. So quickly share the details to all of your friends and various WhatsApp groups. Uh, HG sir, you asked the question how to propose self idea for the article. Yeah, definitely, we'll be having a session on is how to write a research article. In that, we will be covering today is the session on homology modeling. So definitely, I will consider your point. Meena Arul, you not written your city and state. So again, you are welcome. Write down your name of the city and state. So all of you welcome to the channel. Very amazing webinars are also under the channel for the next coming weeks. Every Sunday we are having some webinar. Most probably on the next Sunday we will be having a webinar on virtual lab. So Dr. Satish Kolchetiwar will be then. Shubham Bhaviskar is there from Dhule, Maharashtra. Welcome, Shubham. So all of you, Dr. H.G. is from Pune. Rupali Bratkar is from Institute of Chemical Technology, Mumbai. So, Rupali Biratkar, welcome to this city and state. So, welcome, welcome. And you, if you're not subscribe the channel, just click on the subscribe button and the like button too. So, Sushil Suryavanshi is from Amrutwaini College of Pharmacy, Maharashtra. Great, great. So, welcome, sir. Very shortly we will be having this session, and if every your every like and your every subscribe button is valuable for me, and I'll be using all the techniques and tools and ICT tools are available to improve our session. So if you encourage me by clicking on the like button as well as on the share button as well as on the subscribe button, I will be highly motivated. So I need only your motivation for this one. So my YouTube channel is a completely non-profit, non-commercial, free educational YouTube channel. It is made for the purpose of just serving to the people, because I believe in that service to people is service to God. So Amrita Bhatia, madam is also there. So will you please write your name of the city and your state? So a lot of people are joining to us. Ajay Kumar is there. Ajay Kumar is from Government College, Arts Science College from Aurangabad. So the people are joining from different states. So this is the beauty of this, we can say, online world. Uh, Ninu Fernandez is there from Vimala College of Women, Coimbatore. So welcome, Madam. Amrita Bhatia is from Pune. Yes, welcome all of you. So very quickly, just patapat, write down the name of the city and the state you are from. Dr. Vaidwell Emmanuel is from the Goa. Great. So welcome, sir. Vaidwell, sir, welcome. Amala. Okay. So you can see the people are connecting to us, connecting to each other from all almost from every state of the India. So quickly write down the name of the city and the state your life from. So that will be others will be knowing that how far you are there. Uh, yeah, from Tamil Nadu. Yeah. Then we are having a lot of people. Jayashree Jagtab is there from In next 1 minute, we'll be starting. Write down your name of the city. Is from Sangli. Sachin Puri is from NIMS Mumbai. So welcome both of you. So we are having the great session today. Very shortly, we'll be starting in 1 minute. Okay. So Samir Sheikh is there from MC Allana College of Pharmacy. Mangesh Bhalikar sir is there from AISSMS. Bhalikar sir, welcome to this channel. And Manoj Chavan is there. Good morning, sir. So now we will begin in next few seconds. So Dr. Prajwal, will you please stop the video and come to the presentation? Yeah, great. Thank you very much, and welcome again, all of you. It is a very great session and very wonderful morning to all of you. Myself, Dr. Anwar Sheikh, and today we'll be having a session on homology modeling. So I started this educational YouTube channel far before 2015, but a little bit more active in this COVID era, because you know that due to the social distancing and all, we are stuck at home. But our education should not stuck, our research activity should not stuck, our knowledge sharing should not stuck, because we are having alternative ways through online platforms. So I am starting all these webinar series, and this is my 15th webinar, and which your all support. All the webinars are great and very very successful, and I hope the same type of the coordination, same type of the support I will be getting from you people in the future webinars. The future webinars are on how to create a, you can say, the virtual lab. If you're not having the resources, then how you can conduct your practicals online by using the resources which are having on your laptop. So that will be the webinar. We are having the another great persons, and next to next we are having the webinar on you can say design of expert. Then we are having the webinar on how to write research article, how to publish the research articles. So all the webinars very very useful and general to all. Anyone can be attending. It is not a subject specific. So we'll start today's session.
Yep.
Uh, introduce him to you. Dr. Prajan, this Nandikar is currently working as a senior scientist with Storage Engine Inclusive at Bangalore office. Master's in 2010 and PhD in 2015, respectively. He is the recipient of the most prestigious DAD fellowship, DAAD fellowship, to perform the research at Heidelberg University prior to joining the Scott Engine. He has process. His research interests are computer-aided drug design, quantum chemistry, then multi-scale molecular dynamic simulations. He has been associated with many eminent scientists and has experience in diverse range of the research projects and proteins, DNA as a drug target. And he holds 33 publications with credit in well-reputed and impact factor journals. So this is a brief introduction of Dr. Prajwal. And with this introduction, I will hand over the mic to and session to Dr. Prajwal. So hope during this session you will be at the end. Definitely we are having the question answer session. So don't comment during the session that good morning and something. Don't comment during morning during the session. We will be getting 15 minutes at the end. So now the session over to Dr. Prajwal. Sir, you can continue.
Yes, thanks, Dr. Anwar, for such a nice introduction. So first, let me know somebody like whether I'm audible or you are able to see the screen perfectly.
Someone from the audience, just can you comment if the sir is audible to you or not? Just write in the comment box after sir speak.
Okay,
Yes,
so
sir, you are
I
audible.
think yeah. So I just got few comments. So it's perfectly fine. It seems. Okay, so I think it's time to start the presentation. I hope you have seen some nice videos from Schrodinger. So those were mostly for the promotional purpose, or it also highlights what you can do using Schrodinger and how nicely you can visualize everything with Schrodinger. So that's the motto. Now, other thing is so for today's presentation, as requested by Dr. Anwar, so we are mostly focusing on homology modeling and its application in drug discovery. So before that, as Dr. Anwar already introduced me, so I'm Prajwal Nandekar. So I'm working as a senior scientist with Schrodinger, specifically at Bangalore office. And this is my email ID and phone number. So just for your reference purpose, you can note it down in future. Like if you have any queries related to homology modeling or molecular modeling or computer-aided drug designing, you can always contact me. Please do not hesitate to do it. So, and mostly my topic, I mean, this presentation will be covering on how easily you can do homology modeling using Schrodinger suit. Means you might be using many different softwares, and you might come across a lot of things like you need to know scripting, you need to write various scripts, or there are few software which can give you click button accessibility to do homology modeling. So similarly, Schrodinger suite also has homology modeling modules, and those are pretty easy as compared to other software. This is what is I observed from my personal experience. So there are many such things. Other than that, I will be also focusing on the basics of protein and protein modeling. What are the things which you need to take care of? What are the challenges involved in it? And many more. So with the demo of Schrodinger suite. So without wasting further time, I'll just start the presentation now onwards on homology modeling and applications in drug discovery. So basically, as probably you already are aware of molecular modeling or computer-aided drug designing. So let's see something which is basics of drug designing. As you know, we need to design new molecules against particular target, and it resembles with our lock and key model. I think that's very primitive information which we have. I guess everybody from the field of pharmacy, everybody has this information that how drug binds to the receptor. It follows the same mechanism as that of lock and key model. As key fits in the lock, similarly any drug molecule fits in the enzyme or any biomolecule. You can consider it as a receptor. That can be your protein, DNA, RNA, antigens, antibodies, or any biological molecules in our body. So the idea is until and unless you know what is inside the lock, you cannot design a proper key against your lock. So same thing is same idea is translated into drug protein interaction. So we need to ultimate aim is to design a key, means a drug molecule, and to design a key we must know what is inside the receptor, what is inside the lock. For that we need a molecular microscope. So molecular modeling softwares are considered as a molecular microscopes. So by using this microscope, molecular microscope, we can see what is inside the protein, and in this way we can design a complementary features like hydrogen bond acceptors, hydrogen bond donors, charge group like positive and negative groups, or hydrophobic groups. This is the way basically we design a new molecule based on the complementarity which is present in the lock or the protein or receptor. So in broader sense, our CAD methodologies are divided into two types: structure based drug designing and ligand based drug designing. So structure resembles to the structure of receptor or biomolecule, means a protein. You can say it as a protein. If you know the structure of protein, you can use that information and you can go for further computer aided drug designing techniques to design your better molecule. So these can be your molecular docking, in which you need receptor, MD simulations in which also you need protein receptor complex, and another thing can be homology modeling, in which we try to build a structure of your receptor. So other than that, there are many such methodologies, but also next classification is ligand based, in which basically you don't if you don't have the information about protein structure, then we are bound to use only information from ligand, and that can be used using various methods like 3D 2D QSARs or fingerprint method, shape based screenings. So many of such things are available in ligand based drug designing methods. So we can use that ligand information and their biological activity information for developing pharmacophores or 3D QSAR model. So that's very basic. So here we are specifically focusing on homology modeling only. So before proceeding further, something about how to design a project, means CAD project. So if you are newbie to the computer aided drug designing, so there are few things which you need to always keep in mind before going further for the project or before designing a project. So broadly it is classified into 4 quadrants. So these 4 quadrants belongs to the information available with you, mostly from literature or from any other website or from various sources. So for example, let's consider the first quadrant, in which I wrote it as a ligand quadrant. So ligand means if you have all information available with only ligand molecules. Ligand molecule means drug molecule or active molecules, and you don't know information about protein. So I would categorize it as a first quadrant, ligand quadrant, in which you need to rely on ligand based drug designing methodologies like pharmacophore mapping, QSAR, core hopping, or similarity search, shape based search, or radiometric predictions. So these are the methods in which you don't need information of your structure, means receptor structure, and you can solely rely on the information of ligand. Another quadrant is your protein quadrant, in which if you have only information about your protein structure available and there is no information on ligand, so we can go for various methods like docking based virtual screening, e-pharmacophores, which is energetically optimized pharmacophore, or de novo drug designing, or you can say fragment based drug designing. So these are the methods in which one can only rely on the structure of protein, but that should be optimum enough. Another thing is, if you have information about your protein as well as ligand, means receptor and ligand, then there is a open sky. You can use all type of methodologies like structure based method, or molecular docking, or pharmacophore, or R group enumeration, synthetic pathway predictions, or MD simulation. So there are a number of methods which are available in computer aided drug designing, in which you can use protein plus ligand information. But what if you don't have any information on it? So there are various ways, like if you don't know which protein, if you don't know the structure of protein, then you need to build the structure of protein. So for that we can use information from homology modeling. So in homology modeling we basically build a structure of protein, and once you will have structure of protein, we shift it to protein quadrant. So then you can use all other methodologies. So similar way we need to think These are the factors which we need to consider before designing a project. But all these things are basically relied on the information available. So I would always suggest to have a thorough literature search. Thorough literature search means you should not miss something about your target, something about your project, something about your pharmacological area in which you are working. So the thing is, you should not miss those information from the literature. By any way you need to collect that information. So that's what is the broader sense we need to consider while designing a project, and then you can proceed for the particular type of computer aided drug designing project. So mostly when it comes to the I mean structure based methods, or when it comes to the protein modeling, there are few things which you can do using Schrodinger suit. For example, you can model a protein or any receptor. You can do RNA modeling, DNA modeling, or antigen antibody modeling. So whatever is related to the protein structure or receptor structure, I would say, like biological molecule, you can do all those things using Schrodinger suit. You can analyze the binding pocket. If you don't have information about the probable binding pocket, we can predict it using a sitemap tool of Schrodinger. Even in case sometime if you have a crystal structure available of your target and it is not much reliable because of the low resolution, so we can also have option to refine that crystal structure and use it for further screening. Or you can also do MD simulation methods on your protein ligand complex or protein based on what are the things which you want to address in your project. So now we are coming more towards specific about homology modeling, or about the protein. So let's say broadly we are doing homology modeling to develop a structure of protein for which we don't have experimental information available from protein data bank, means there is no crystal structure available for it. So basically in the basics of protein, you need to see like how protein is made up of. So basically protein is made up of 20 natural amino acids. So there are few modified amino acids are also there. Mostly it is from 20 amino acids which are naturally occurring in our system. So and all amino acid residues are linked through peptide bond, and together it forms a complete structure. So if you see step by step way, like what are the nomenclatures of it, like whenever you have just a sequence of protein, sequence means the this alphabetical representation of protein sequence is called as FASTA representation, in which we use simple single letter code of amino acid residue, and a structure associated with it is can be, we call it as just a primary sequence. So because it doesn't have any structure or secondary structure information with it, so we call it as just a primary sequence, just a single letter codes. But when these all residues come together, they form a energy minimum structure with some secondary structure elements, and those are kind of either alpha helix or beta sheets. So we consider it as a secondary structure. So onwards, like whenever you come across these terms, so these are secondary structures, alpha helix and beta sheets. And some are there also distorted things. So those are considered as a loop. So basically it provides a particular stability to your structure. So when all those secondary structures come together, they form a tertiary structure, and tertiary structure is your protein, which you can see in the visualizer, or you can find it from the protein data bank also. So it has particular function. So tertiary structures are mean for some particular function, like its enzymatic activity or its role in a particular biochemical pathway. So for that we require tertiary structure. Sometimes also there are big assemblies in which a lot of tertiary structures come into contact and they form a quaternary structure, means big type of structure. For example, viral capsid, or actin, means fibrous proteins like actin, myosin. So those are considered as a quaternary structures, so which are mostly related to the big assemblies. So this is just basic introduction about the structural components of the protein. And now comes to the various methods of structural determination That's mostly experimental. So you can have a structure from your experimental studies called X-ray crystallography, in which we can have atomic resolution model of a protein with some resolution, like 1, 2, 3 angstrom, something like that. Then but X-ray crystal structure is always a rigid one, a rigid crystal structure. You can have only resolution of each and every atom, means electron density maps. Then there comes NMR structure, NMR nuclear magnetic resonance structure solved by NMR method. So you can see basically it is a solution form of structure. So that's why it consists of a lot of ensemble structure. So whenever you look into the NMR salt structure, you will find the ensemble. So it's not a single structure, just like a crystal structure. It will be lot of conformations present in the same structure. So you need to carefully use which conformation I want to go proceed further with. And the limitation of NMR is because it's a solution, it's highly dynamic, and the size of structure is really limited to 30 kilodalton or less, means around 200 residues of a structure. You cannot solve more than that amino acid residues using NMR. There is also another experimental method called basically electron maps. So in which you can see you have a big structural assemblies which are present in which are solved using EM methodologies. So so I mean mostly these structures has a higher resolution, like 3 angstrom, 5 angstrom kind of resolution, but you will able to solve the big assembly, protein structure assemblies using EM method. So these are the general things which you will find in protein data bank or other type of repositories, structural repositories. So which are those? Like we know about protein data bank, but that's not alone. Like there is also European protein data bank or Japanese protein data bank. So these are the various databases which are available for you to get the information about structure, which are crystal structure, animal structure, or EM structures. So we can have those structure. You can have those structures from various these databases. So so the idea is we should know which are the databases or repositories available for this structural information. So one should not really confine themselves to only one database, for example protein database, but there are others also. You need to look for all possible information. That's the idea. So whenever when to go for homology modeling, so the straightforward answer is whenever you don't have the structure available for your protein structure, for your particular protein, means experimentally determined structure, then only we need to go for homology modeling. But if it is available, so in that case it is better to proceed with the experimentally available structure. So how to do it? We should have a suitable template, which is basically a homologous template from same family of protein. So that information we can use to build a reliable homology model. Something into the basics of homology modeling. So term itself indicates like homology modeling. So homology means something which is homologous. So the idea is you want to design a unknown structure basically from the sequence of amino acid residue by using a template which belongs to the same class or family of protein. So if you have a good kind of template available for your known sequence, so the idea is if the sequence matches, means if the sequence is comparable, then structure can also be comparable. That's the crux of homology modeling. So I mean the hypothesis is whatever, if sequence is identical, then structure should also be identical, and we use the same concept to build a homology model. So you can see there are various type of templates available for a lot of different type of proteins, like kinase proteins or GPCR protein. If you have that suitable template, we can easily build a new model based on this template. So the idea is sequence similarity is equal to structural similarity. That's the only basics of homology modeling. template based homology modeling. So in general, what is the protocol which is followed by any software, or you also need to follow the same procedure or protocol to build a reliable homology model of a known structure. So first of all, you need to have a sequence of your target protein. So target protein here, I will consider this term afterwards as the protein for which you want to do homology modeling. We call it as a target, and the reference structure we call it as a template, means for which we already have the structure available in protein data bank or other databases. So first thing is you need to retrieve the amino acid sequence, that is your primary sequence, from sequence databases, and one of the popular database is Uniprot. So you can directly go there and check for whether a sequence is available. If sequence is available, then you can proceed for homology modeling. But what if sequence is not available for your protein? Then to be frank, you cannot do anything with the structure. But there are other methods like bioinformatic genome based. You can basically, by using genomic sequence, you can decode the sequence of protein, but that's not pretty much reliable. So consider, if you have a sequence available for your target protein structure, then only proceed for homology modeling. So once you get the sequence, the next task is to identify the suitable template. For that, we need to perform BLAST-P search against the protein data bank or structural databases where the structures are available for protein, means experimentally determined structure. So after doing BLAST-P exercise, you will have the list of various templates, and out of that list of template structures, you can choose basically the best suitable template based on various factors like sequence identity or sequence similarity. Then how much is the query coverage, means how much it covers for the alignment. Then whether it consists of any missing residues, what is the resolution of this particular structure, whether it is present with ligand or without ligand or cofactor. So these are the various factors which you need to consider while choosing a suitable template. Once you will have suitable template, you need to align those two sequences perfectly. That is very critical in homology modeling, means the sequence alignment. So you can use various techniques like single sequence alignment or multiple sequence alignment for the best sequence alignment, or you can also use secondary structure prediction, in which it will perform sequence alignment based on the secondary structure elements present in the protein structure. For example, alpha helix of the template structure should align to the alpha helix, predicted alpha helix of your target sequence. So these are the factors. Once you will have target template sequence alignment, which is perfect one, we can proceed for the homology model building using prime option. So in homology model building also, we will have different methods like knowledge based methods or energy based methods. And so what do you mean by knowledge based method? Means whatever information is available from the reference structure, means template structure, it tries to model the same thing in your target structure. Or energy based method means it will energetically optimize the structure or your target structure based on what is the energy of these residues. You can also consider ligands in your homology modeling, or ions or cofactors or whatever it is. So there are many other options available, like you can build separately a backbone of your protein structure. You can predict side chains if the information is not available with the template structure, or you can also add or remove few residues if it is not present in your template structure. So those are various things which we can do using prime homology modeling, and these are the factors you must consider it before proceeding for homology modeling. Then once you will have a model, the critical thing comes into picture, like you need to check your model or you need to validate your model, whether it is good model or bad model. So if it is good enough based on our required criteria and parameters, then you can proceed further. If it is not good, then you need to go back again and build several models. So what are the parameters you should consider? So there are a lot of whether there are a lot of steric clashes present in it, and you also need to check whether how the Ramachandran plot looks like. There should not be any disallowed amino acid residue torsions present in the Ramachandran plot. Then what is the RMSD between target and template? Whether binding site is modeled correctly or not. That these are the things which you need to check, and all those things are automatically considered in the protein report or protein reliability module of the Schrodinger suite. So in just one click, you can get all that information. You don't need to go to any other software or any other server to check the quality of your model. Similarly, to refine your model, you can also perform loop refinement or energy minimization based on the things which are looking bad in your protein structure. So this is the general protocol which you need to follow till you get a good quality of your model based on all those parameters. So that we can use it in the homology modeling software. So I mean, as I already explained, like it's all because it is template based homology modeling, so it is based on template. So you can have target sequence, you can have a template sequence. We align those two sequence and check how good it is aligned. So we take whatever information is available from your template structure, and we try to mimic that all information in your target structure, and in this way we build the tertiary structure of your target protein. So, and if it is good enough, we take it further, or if it needs refinement, we again go back to the model building and try to refine it. So there are few things which you always need to consider, like you should have a good template structure. This is very critical as it is the first step of any homology modeling, so that should be correct enough. Then the sequence alignment is also critical one. I would say very crucial. So you need to have that sequence alignment done perfectly. Other thing is, while building model, you should choose the correct force field or reliable force field to generate an accurate model, because force field is necessary for consideration of all type of interactions which are present inside the protein structure. So those interactions should be correctly treated. Until unless you treat those interactions correctly, you will not get a correct structure as an output. So so I mean, there are various methods to choose a good template structure. First of all, you need to have very good kind of template from protein data bank. It should have good resolution. So once you have this template structure, so whether it is that much reliable or not, if your work is getting done by single template, that's well and good, but sometimes single template is not enough to completely cover the target sequence, or because of some residues are missing, because of some domains are missing in the crystal structure of template. So you can also choose the multiple template structures or multiple or consensus modeling method, in which we can use various type of different crystal structures as a template, and we build a multiple template model or consensus modeling. Means we learn from all available template structures, means multiple template structure, let's say 3 or 5 template structure, and we try to build the same thing in your homology modeling. This is again very much very rare cases, but if your problem is not solved by single template model, which is always recommended, so you can go for multiple template modeling. Similarly, you can also generate a composite or chimeric model of your protein structure. For example, there are two homologous protein which differs only by few residues, like 4 or 5 residues. In that case, you really don't need to build a complete homology model of a protein. You can simply build a chimeric model in which you take only that different part of structure and copy it into your target structure. That is called as chimeric model. So similarly, there can be a case in which you need a dimer you need to build a dimer model or multiple model. So there are many such proteins which exist in a active dimer, trimer, or multimer. So whenever we say dimer, trimer, homodimer, or heterodimer, so means either it can be the same unit or it can be different unit. So we can also build such type of dimer or multiple type of models using Schrodinger suite. So other thing is related to GPCR proteins or membrane bound protein. Those basically protein follows specific fold, and it needs a very specific treatment. So that's why we have also included GPCR specific modeling in our Schrodinger suit. So you will have that option available. Then in case of loop modeling, we will have a loop modeling option available that also you can use. So the thing is, all type of possible type of homology modeling methods are all covered in the Schrodinger suite prime module. So you really don't need to look into any other software or any other server to build your model. And again, it's pretty reliable in case of all type of such model generation. So you need to decide which method you want to go further with. So next thing is sequence alignment. So as you can see here, these are all homologous protein in which you will find most of the residues are common. So you need to have such type of alignment before generating protein structure. This is basically a sequence of kinase proteins, and you can see in kinase DFG loop is one of the critical loop present in binding pocket, and you should have all residues aligned perfectly until and unless it gives you a perfect alignment looking like this. uh, I would not suggest you to go for homology modeling because it will not give you that much reliable results. So next thing is you also need to consider the biological activity of bound ligand for this particular protein template. Like you want to model an active form of protein, or you want to model a native energy minimized form of protein, that you need to think. So for example, for any drug designing project, it is always better to go with the template which consists of the most active ligand bound in the protein structure. So this is one of the thing which you need to consider before proceeding for homology modeling. So next method is force field. Force field is also one of the critical parameter, and according to Wikipedia, force field defines basically the parameters for potential energy of your atoms or molecules present in the structure, which consists of various bonded and non-bonded terms. And based on that, it tries to model the atoms or molecules or residues in the protein structure. So just a little bit in detail what force field governs is. Basically, force field governs how two atoms are bound to each other, whether it is through covalent bond or non-covalent in type of interactions. It also governs the what could be the angle between three atoms, and we call it as a harmonic angle because it is in continuously motion. So similarly, it also governs what could be the torsion angle between four atoms. That is also critical to understand. And what are the interactions, basically whether these are van der Waals interaction or electrostatic interaction between two atoms, those are also governed by the force fields. So ultimately, from these interactions, various type of interactions or various type of angles or distance or dihedral angles, we get energy for this particular system, and this energy can be converted into force. And this is what is the basics of basically force field. So why you need force field, good force field is it is because it is all about modeling a new structure for which you don't have any information available experimentally. So we need to model it correctly. So to model it correctly, we should have, like whenever it models, it should have the optimum type of interaction between between residue and residue. So you can see like here how it is modeled using different force field, and we need to consider which conformation of the residue should be there to have a energy minimum model, or to minimize the energy between two residues. So it's not only about two residues, but it's about the complete structure. In structure, everything should be at energy minimum level. So you need to choose this force field critically. Other thing, whenever we build homology model, so the one of the again important thing is the solvation model. Means, as we know, like this in body we have 90% of water, and whatever protein we talk about, it is either present in cell cytoplasm or in membrane. So that's why, I mean, the environment affects a lot on the structure of protein or the folding of protein structure. So that's why, for just as an example, if your structure is present in cytoplasm, means mostly it is surrounded by the water molecule or polar solvent. So in that case, the effect of solvent also needs to be considered. The ideal thing is explicitly you need to consider water molecules around your protein structure while building the model. But because it's very much computationally expensive, this method we call it as a molecular dynamic simulations from ab initio. So but that's very much computationally expensive. So what we do trick is we use implicit solvent model. Implicit solvent model is nothing but like we apply the dielectric constant of surrounding medium at micro level surrounding the protein structure. So you can see it is basically a grid based method in which it doesn't use explicit actual water molecules, but consider the dielectric constant of that medium. And based on that, it calculates the folding of protein, or it considers the effect of solvent on the protein structure. So even so in Schrodinger we mostly support VSGB model of we have, this is what implicit solvent model which we have developed, and we have been using it in our modules, and with the OPLS3E force field developed by again Schrodinger. So if you see like how it performs well, so here in this table it shows the loop length, means the length of loop, let's say from 14, 15, 16 amino acid residues long. So even you have that much such long loop region, and we have implemented this method on various structures to predict how correct it is. And you can see the average backbone RMSD of all these cases lies within 1 angstrom, or for longer longer loops like 18, 19 or 20 residue loop, which is very very long. So it also limited to less than 2 angstrom, means it is pretty reliable. And you can see like for a number of percent of cases which are studied through this method are even almost for all of the cases, like majority of cases, around 90% of cases, the RMSD lies within 2 angstrom. So it means it ultimately gives you the better reliable model as a for your protein structure using this implicit solvent method. And I would say that's very very critical. You should get a reliable model using implicit solvent method, otherwise that method is of no use. So thing is another thing is loop sampling. So there are various methods which are available in loop sampling, like for example you want to refine multiple loops at a time, so you can go for cooperative loop sampling methods. So the option is present here in loop modeling, like so it automatically refines multiple loop structures at a time to check the effect of each and every conformation of all loops on each other. So that's called as cooperative loop sampling. Another method is serial loop sampling, means it will proceed from, let's say you have 5 loops which you want to refine. So you if you want to refine all loops at a time, we can go with cooperative loop sampling method. But if you want to refine each loop at a time, we can go for serial loop sampling. So first it will refine loop 1, then go to loop 2, then go to loop 3, then go to loop 4, and in this way. But in cooperative loop sampling, it will simply refine all loops at a time, just to check what is the effect of it, effect of all loop conformations on the complete structure. Then there are 3 with basic levels of loop sampling, like default, extended, and ultra extended. So what does it mean? It means like how many amino acid residues are present in the loop. So for example, if loop is short, which you want to refine like less than 5 residues, we can go with default method. But if loop is long enough with like 5 to 10 amino acid residues, then you need to go for extended loop sampling method. If it is more than that, we need to go for ultra extended method. Means it basically gives more extensive calculations, more extensive loop confirmations explorations. So based on that, we need to go select particular loop which is of our interest. So these all methods are basically available with Schrodinger suite. You will see how it looks like. So again, the thing is, whenever we talk about loop sampling, because as loop goes bigger and bigger, it has lot of degree of freedom. not only degree of freedom, but it might have lot of different conformations, and to sample all those conformation we need huge computational power. So I would say loop modeling itself is a I mean computationally expensive method than complete homology modeling. So based on template you can build a homology model of any protein, let's say 300 amino acid residue protein, in few minutes, but it requires few hours to sample various loop conformations, means in loop refinement. So these are the computationally expensive calculations. So but again, to refine your structure we need to go with such loop modeling method with reliable method. So that are the things which you need to always consider while proceeding for the bigger loops. I would say one can easily refine loop with less than 5 amino acid residue, but if it is bigger, you need to have that computational power, which is also related to the time required. So there are a few challenges which I have found from my personal experience. Like these are the various challenges which you always come across while doing homology modeling. Like as I already explained, it needs good template. It should have good alignment. To get a good alignment, you should have good sequence identity or similarity. If everything is fine, then you will definitely get good quality of structure. But if it is a low sequence identity thing between target and template, then it is tricky, little bit tricky. So you need to try multiple times to see. And again, because if it is in case if it is low sequence identity, you need to rely on your intervention, whatever basically your knowledge about the protein structure. You need to use all that information while building a model. Another thing is about for example the residue conformations, which can be your for side chain predictions. We have rotamer packing, that also you need to carefully look into it whether it has packed correctly. There are many distorted structures which are mostly loop. Those structures you need to refine. In case of if there is misalignment between target and template, you need to basically align it properly. You need to look into those factors. Then comes the model refinement. You need to refine your model using energy minimum conformation. You need to refine the side chains or loop conformations, or mostly if you are dealing with drug designing project, we need to really take care of binding site conformation, because that is also very important for you. Then I mean it all comes to the mostly most of the things are getting solved if you have suitable template with a high sequence identity. So but if it is not that much, then we need to rely on few parameters. Like if you have more than 70% of sequence similarity, you will quickly get the homology model. But if it is like 50 to 75% of sequence identity, then you need to fine tune little bit your model, and you need to perform loop modeling also. If it is less than that, 30 to 50, you also need to correctly alignment your model. You need to check it at each and every step. So that's with a lot of human intervention. And if it is less than 30%, then definitely it's become tricky, and you need to check at each and every point whether it is correct. If it is not correct, you need to make it correct based on your knowledge or experience. So these are the various challenges which we always come across homology modeling. So next thing comes, like I have mentioned about protein quality report. So basically this is the option which is available with Schrodinger. In just single click, you will have all possible parameters for the protein structure, which you can use to check whether your model is reliable. For example, Ramachandran plot, that you can check with dihedrals of amino acid residue should not lie within a disallowed region. Then there are various type of deviations, steric clash, like bond angle deviation, bond length deviation, dihedral deviations, or not suitable beta factors, or there are steric clashes. So there are many such parameters which you need to analyze for the reliability of your homology model. So you can get it in just single click. Other than that, there is something called a report, complete report, in which in just one view you can get all information about those parameters. For example, it basically analyze your structure, and it looks for various options, like as we discussed, protein packing, loops, water, whether it is present, what about the binding site residue, what about non-binding site residues, what about steric clashes, side chain dihedrals, and all other things. It just look holistically into all parameters and give you the complete picture in just one go. So here whatever is present in a green means it's all and good, well and good. If it is yellow means you need to look into it, and if it is red means you need to basically refine this particular red region. So for example here in this particular image there is a red circle in steric clashes parameter. So basically you need to look into steric clashes of this particular protein structure, and you need to refine those steric clashes, most probably using energy minimization of the structure. For that also we have option. So this is what is about various basics and theory of your homology model. And now we will quickly see how it looks like on the Maestro interface in Schrodinger suit, and we will try to develop a homology model of human phosphoglycerate kinase 2 protein based on the suitable template, which is again its close isoform, which is human phosphoglycerate kinase 1 structure, for which we have a crystal structure available with protein data bank. So let's see it on the interface how it looks like. So I'll just start Maestro. So we will have Maestro icon here present on, let's say, on your desktop. So you just need to double click on it. It will open the Schrodinger suit, and once you have a Maestro interface open, so we will see how it looks like. So I hope you will find it user friendly, or we can also have various training videos on how to use Maestro interface. So this is how it looks like. This is the black color region, which we call it as workspace. So here you will able to see all type of your molecular models. So first thing, whenever we open the Maestro interface, first thing we need to do is we need to select our working directory. Working directory is nothing but the directory in which you want to work, and you want to store all of your data onwards related to your this particular project. So I'll just change this working directory to somewhere reasonable. Let's say desktop. I'll create one directory, for example homology modeling. Try to avoid giving space in the name of folders. You can use hyphen or underscore. So let's say this homology modeling, that's my basically a working directory which I'm going to choose. So just click on choose. Once you choose your working directory, you will see on the top here you will get the path of your working directory. So this is the directory where your all of data is going to be stored. So next thing is you need to save your project, because you don't want to miss whatever is you are doing. So for that you need to save your project, and mostly you should save your project in the working directory with some reasonable name. So for example, I'm just giving project name with homology model, and it will be saved in .prj extension. So this project is basically resembles to your let's say you are writing a manuscript and it's just a document. So whatever you write in it, you need to save this particular document, so that after 10 days if you want to edit something or add something, you should not miss all previous information. So that needs saving, continuously saving your model, continuously saving your document. But with Schrodinger you don't need to save it again. Once you have saved your project, it will be automatically auto saved now onwards. So now onwards whatever I will do with this project, it will be automatically saved with it. So even after 10 years if you open this particular project using this file and open project option, it will remain at the same place where you have left it. So that these are the two critical things which you need to do whenever you want to start with the Maestro. So now proceeding to homology model. So first thing which we need is basically a sequence of amino acid residue. So for that the best option is search into UniProt database, whether sequence is available, whether structure is available. So this is how UniProt database looks like. And because I said I want to go for homology modeling of phosphoglycerate kinase 2 protein, so first thing is I need to look whether crystal structure is already available or whether amino acid residue sequence is available for it. I'll just type query correctly like phosphoglycerate kinase 2 protein. So I'll try to write it as perfect as possible, and it gives me various options for phosphoglycerate kinase 1, phosphoglycerate kinase 2, and I want to look for human structure. So this is what human phosphoglycerate kinase 2 protein. So with this entry, I'll just go to the this particular page of this option like human phosphoglycerate kinase 2, and in which basically all of the information which is available so far is already presented here, like what is the name, subcellular location, what is pathology, what is biotechnology of it, and all other information available with it, in which I will look for whether structure is available for it. So in structure section, I will have, you can see here in the structure section, there is no link for protein data bank. So it means there is no crystal structure available for it. If it is there, it must have given you the various links for the uh, structures available. But currently nothing is available for this particular protein. So next thing I will look into the sequence. So what is the sequence available, whether it is available for with me or not. So it says like sequence is available, and so here there are number of residues. For example, this length is 417 residue long and protein. So now sequence is available, structure is not available. So it means this is the perfect case. I can go for homology modeling. So I'll just download the FASTA file for this particular sequence. I'll store it in some local folder. So for example, just save it in my working directory. For example, I have created a directory called homology modeling, in which I'll just store this particular sequence in FASTA file, in FASTA format. Let's say, give some name, which is identifier for you, and save it. So once the sequence is saved, now the first thing is done. What you need to do now, you want to build a homology model of it. So what I will go into, I will go into task, because in this task you will have all possible available options with Schrodinger suite. Now I need to look for particular module for using which I can build a homology model. So every time I used to say about prime homology modeling. So prime is the module for homology modeling. You can find that option here. In prime, there is an option called homology modeling. In this particular homology modeling panel, you will have two options. So one is multiple sequence viewer, and the hint is also given like when you should use this option. Like it is ideal for those who are already familiar with homology modeling, and if you wish to perform multiple sequence alignment. And there is another option like structure prediction wizard. So it is pretty simple, and it is ideal for those who are new to homology modeling. So I'll just go with this option, select on it. It displays a panel. So this is pretty straightforward panel. In just few steps, you will have homology modeling done. So the first thing you need to do is you need to load your sequence, and you can do this using option get sequences from your file. So let's say file. I have this first file saved. I just open this particular file, and it will show me all possible information available with this master file, means what is the sequence. And you can see as I move mouse on the sequence, it also will show me the number or what the residue is. So it's all interactive. At least this is very good thing with Schrodinger, like every panel, everything is interactive. You can have all information available. You can know all information available with that particular point by just moving mouse on it. So it also shows me what is a uniprot ID, what is name of the protein, and how many amino acid residues are in the protein. So that's the information which you can easily get from this panel. Once it is done, it's done. You just need to click on next. Next is always present on the bottom right. So the panel is done. You just need to go to next step. Next step, you want to search for the homologous proteins which are present in the protein data bank. For that, you just need to click on this blast homology search option. It takes some time to load. Once you click on this blast homology search option, it basically uses the web server Means your computer should be connected to internet. It will look into all possible structures present in the protein data bank, and it will give you the possible template structures. Based on that, you can choose which one is the best suited structure, template structure for you. So it's just pretty straightforward. You just need to click on last homology search, and it does the things for you. So for example, um, because it takes some time, so I have already run this job, and you will get the result in this particular format, in which you will have the once this job blast search get finished, you will have all information in tabulated format. You will have various PDB IDs, chains, then the name of this particular structure, then what is the score, how much is the identity, how much is the sequence similarity, we call it as positives. Then what is the title of this crystal structure, whether any I mean the this which class it is belonging to. Then what is source of this particular structure, like Homo sapien or any other organism. Then which is the method of solving this structure, like X-ray, NMR, or cryo-EM. Then what is the resolution of it, then what is whether ligand is present in it, whether cofactor is present in it, or if there are any missing residues present in it. That all information is available with this with you on just single click. And as you select the any template structure, it also automatically align that structure and show you in different colors. So you can see there are various protein structure with same type of identity. So you can simply click on various other structures. If you feel like I should not go with the first one, but I want to go with second one, it automatically updates the sequences in the top panel for you. In this way, you can go with all other templates, basically whatever is present in this table. So mostly I feel like 87% of sequence identity means this is the crystal structure belonging to same family. So I'll go with, let's say, first entry, because it is well reliable. And if I see the name of this particular protein, I will find that this basically this protein structure belongs to the same class, just another isoform, like phosphoglycerate kinase 1 isoform of the human. So that's why it has very high sequence identity, and it is also bound to the ADP cofactor in it. So I'll just choose, let's say, the first option, but you will have option to select one or any other template or multiple template just by selecting it, selecting multiple proteins at a time, and that will be your multiple template homology model. So for this exercise, I'll just go with the single template homology modeling. Once I select the structure, we just need to click on the next option, again bottom right. So once you click on next option, it will select the particular template, and you will have information only about the selected template. Then there is a align button through which you can just align your sequence if you feel like it is not well aligned. So there are also advanced option, like it also predicts secondary structure element for your amino acid residue sequences, and based on sequence secondary structure prediction, you can align your sequences. As I said earlier, there are various method of sequence alignment. If you want to edit your basically the sequence, there are advanced options through which you can edit, mutate, or you can crop the sequence which is of no interest. So you can do all type of modifications in your sequence using this panel in just a single click. And if I'm done with it, I'll just go to next. So again, bottom right, next. So this is the final panel, which shows like in this pink color, this is my template structure, and white background is the target sequence for which I want to do homology modeling. So you can see here, the bottom is crystal structure, upper one is the name of your target sequence. Then you need to choose which method you want to go with, like knowledge based method or energy based method, as I told earlier. And the most surprising or good thing, I must say, like as I said, every option is interactive. So you just need to move your mouse on this particular option, and it will give you some information or hint about what does this option means. So because it is a high sequence identity template, so I'll go with energy based method. And whether you need to consider a cofactor or ligand in it, it is also pretty straightforward. You just need to select this particular ligand which you want to import, or if you don't want to import, that also you need to think of. And as you see, like, there are many other options available with it. For example, you can go with the chimera generation, or you can choose a homomultimer, or consensus modeling, or there are heteromultimers. So these all options are present with it. But right now we will not go with all those options. We will go with simple home knowledge based modeling, which is pretty faster, and you just need to click on build model. That's it. Like, in just 3 clicks you will have a model done starting from the sequence. We have done just 3 clicks. For example, let's start from here. So before that, you loaded your structure, then next, then again next, and that's it. And finally you just need to click on build model. Once you click on build model, within few minutes it will generate the model structure for you and automatically load it in a Maestro. So you can see the model is already generated in the Maestro interface, and you can see the name of this model also represents something like the sequence of target, the name of target, and homology model built on this particular ID 2ZJV. So basically name itself indicate that this is the model which is generated, and it shows you something in different colors. So those color schemes are also saying something. So for example, you will have such a color scheme in which this dark blue color is for the structure which is generated with the identical residues which are present in the template structure. So those are all colored in blue. Then there is something cyan color, or you can say light blue. So these color represent the amino acid residues which are not identical, which are similar in the sequence alignment. So those are reported here in cyan color. And there is something also present in loop, this particular loop in red region. So red region is always considered as a alert. You need to be alert about red. Red means this is the structure which was absent in the uh, in your template structure, means the crystal structure, and now software has built this particular loop in software has built this loop by their own method. So that's why it is shown in red. So you need to look for whether there is anything bad in it. So we will have let's say the best possible is Ramachandran plot. That option is again present in task browse, and you will have structure analysis section. In structure analysis section, there are various options available to analyze your structure, and out of which I'll just go with the Ramachandran plot. And Ramachandran plot of this particular structure, if I see, so you can see the most of the residues are already present in allowed region except this particular residue. And as I said, it is all interactive. So once you move your mouse on this residue, on the top you will see like which amino acid residue it is. Basically it is on the top of panel. If you see, it is alanine 377 residue. So the thing is, again, it is interactive. So if you simply click on this particular residue, it will highlight that particular residue on the interface, and you can see whether this residue belongs to any region. So this is particular residue which was present in the loop, and because of the distorted structure of loop, it might end up with the disallowed region. So our task is to refine this particular residue, because rest of the things are already present in allowed region. So that's why we don't need to really take care of other residues, but except this alanine 377 residue. And you will be surprised to see there are few triangles or square representation. So those triangles and square are the residues. You can see these residues are glycine and proline. So those residues are exceptional exceptions in the Ramachandran plot, that they can be in the disallowed region. So we really don't need to care about these triangles and other squares. So for example, this kind of square for, so means glycine and proline are exceptions in Ramachandran plot, but whatever is mentioned in dots, like these black circles, that you need to take care of. So this is how you need to look into Ramachandran plot. Then there is another option called, as I said, like protein reliability report. So in this protein reliability report, you just need to analyze the complete structure. So here is the option, analyze entire structure, and you just give some job name and click on simply run. So in just one single clip, it will run everything and it will analyze all possible things for you within few minutes. For example, I have already analyzed these things and put it into reliability report. So you can see, so you get such kind of view in which all other parameters are automatically analyzed, and the parameters which you need to take care of are highlighted in red color. So for example, this particular structure has a lot of steric clashes present in it, and peptide planarity is also a problem. So you need to consider these red color options to for improvement, for further improvement. So let's say I will just go with this particular option, and we will see how it basically improves. So to get rid of steric clashes, I have simply performed energy minimization on the structure using again the option which is present in protein structure, protein preparation and refinement. So in that there is an option called energy minimization, in particular protein refinement section. So I have just opened this panel. So as I already discussed, there are various type of solvation models, implicit solvation models we have. So you can choose any of it, like implicit solvent or vacuum or chloroform. Then the force field, which force field you want to go with, it should be reliable enough. And you just need to click on the run, like it automatically perform energy minimization of all your protein structure and give you the output. So for example, after performing energy minimization, I got this particular structure as a output, which is now in little bit different conformation as that of before. So you can see I have loaded on the top of two structures. Like first one is uh, first homology model, which I would say crude homology model, and then energy minimum structure. So you can see there is a lot of conformational changes happen in the structure. And now my task is, I again need to go into protein reliability report and look for what are the basically what are the things which has changed now, and what are the things which are pretty reliable. So I'll just run this protein reliability report again, and I get it as output as for protein reliability report. And you can see now other things are refined. For example, steric clashes, before it was red, now it is green. These steric clashes can be easily refined using energy minimization, but the peptide planarity is still there, that I need to consider somehow. So this is the way, I mean, then next things also come into picture is the loop refinement. So you will have a structure for your loop refinement. So again, for loop refinement, what you need to do is you simply need to load your structure, and there is an option called loop refinement in your prime. So in prime there is an option called refine loops. So if you simply click on it, it will open this particular panel. Again, the options are same, like implicit solvent and force field, these are by default click. So it also gives you the interactive option, like which loops you want to refine. So I have option to select like either non-template loops, which is mostly highlighted here in red, because that loop is not present in template structure. Rest of the all loops are already present in structure, so these are reliably built. So I will just click on this non-template button, and it gives me what is this loop region. So this is considered as loop 1, and it belongs to chain A, and starting residue and ending residue. So it would be like 11 residues present in this loop, and it is automatically highlighted in on the Maestro, means the interface. And you can see this is the loop region, which has again residue 377. If you remember, that was the residue present in disallowed region. So I could refine this particular loop to see what are the various other confirmations for this loop are available. So I just need to select this particular loop, Or in this way you can select basically multiple loops at a time. And as I already showed, there are many different type of options like cooperative loop sampling, if it is multiple loops present in your structure which you want to refine, or if you want to refine those serially, means one each time, and then it is called as serial loop sampling. Then there is a method like you want to go for which type of method, whether default like less than 5 amino acid residues, if it is present in loop you can go for default. If it is like more than 10 you can go for extended, or if it is more than that you can go for ultra extended. So those are the options which you can use, but basically those all options are automatically on, so you don't need to worry about it. One of the very important option which I would like to show is the environment. So there is default environment for your structure is your implicit solvent. But if you are dealing with membrane bound proteins like GPCRs or ion channels, we will have also option for implicit membrane, not only solute but membrane. So it will consider the environment of membrane while refining these loops or the protein structure. That's very, very critical, which gives you a really reliable result. Or it also consider the whether it is a crystallographic unit or not. So these are the, but by default, like for globular protein, this default option is fine. You can go with. So ideally if you see like you just need to click on non-template region, it will automatically identify the loop present in it. You just need to select which loop I should go further for refinement and click on run. Means just I would say single click button thing, you will have the refined loop structure, but remember it is computationally expensive, so it would require some time. So once it is refined perfectly, so you will have the refined structure with you. So for example, I have already done refinement and this is what the structure is. If I compare this particular structure with my previous model, so you can see now the conformation of loop is changed. This now it is going towards more energy refined loop conformation. But as you can see, the other structure of the protein is remains same as it is perfectly superimposed, except this particular loop region in the loop refined structure. So if you see like again, if you go to protein reliability report, which I have already run, and I have already loaded this protein reliability report for this loop refined structure, and you can see like it did not change much, but still a lot of many of options are already green, but there are something like peptide planarity, that option is still in red. So somehow I need to refine that particular option. So I have again performed some, let's say I have performed protein preparation wizard on this particular loop refined model. So for protein preparation wizard, we have option here, and through this option, basically we can prepare a protein structure reliably using this all options like energy minimization or optimization of internal hydrogen bonding networks. So it is also pretty straightforward. You just need to open protein preparation wizard and click on optimize and click on minimize. It will refine your structure. Once you refine your structure, you will get a final structure like this, which is again little bit refined than the loop refined structure. So I hope it is refined now. And then I again run a protein reliability report for this particular structure, and I found like this is the report for this refined model, and let's see how it looks like in protein reliability report. So now you can see this particular peptide planarity is now reduced to something small, but still it is red. So we can again perform energy minimization and see, try to refine what is why it is still red. So if you want to know what are the residues which are giving you this problem, so if you simply click on it, on right hand side you will see like there are three residues which are present in the structure, and those are having problem. So but out of that like glycine you can ignore, align you can refine, and isoleucine you need to refine separately. So these are the various steps through which we can refine our homology model using all other parameters. Then one of the again critical parameter is binding site, because we want to use this homology model for binding for computer aided drug designing or docking. For that we need to have a profile binding pocket which should be similar with the template. So for example, I'll just go with particular, I'll show you how ligand is specifically present in the protein structure which you have refined or homology model. And I have just loaded also the template structure in green color, and you can see the position of your ligand is almost same but more refined for this particular homology model. So green is the ligand position from crystal structure, and magenta color is the ligand position from homology model. So it means somehow the binding pocket is also conserved for your homology model, and ligand is also modeled perfectly as it is ADP. So it has a lot of flexibility present in it. So there can be little bit difference, but if it is a organic small organic inhibitor or your drug molecule, it will be perfectly modeled. So these are the various things which you need to take care while doing homology modeling. So if you see like a basic steps of it, so it's a retrieval of a uniprot sequence, then searching a suitable template using BLAST. Then there are parameters like sequence identity, sequence similarity, or ligand present in it, or resolution of the template structure for the selection of suitable template. And that's it. Once you will have suitable template, align it and go for the build model. So you will have the homology model with it. It is always suggested that whenever you go for homology modeling, try to build as many as possible homology models, because again the thing is because one should not rely only on single model as an output model, but you can generate 10 or 20 models at a time and compare all those models based on all those parameters like Ramachandran plot or protein reliability report options. So these are the things and steps which you need to follow with the homology modeling. So I hope you got information about homology modeling. And now coming back to the uh, our presentation. So at the end, means I would like to highlight the help option. Means with Schrodinger, you will have the help option present with you. So any question, if you want tutorials or manuals, or if you want to know about any option, you will always have this help option with you. You just click on help. It will open the complete manual tutorial, and you can just simply using the search option, you can search for the query just like Google search. For example, I want to know about homology model, or what is implicit solvent, or what is it all answers. Possibly it will answer all of your questions, but if it is not there, you can always contact us. But most of the things are already present there in our manual. So similarly, like to deal with the protein, we have protein docking, protein peptide docking, residue mutations, alanine scanning, cysteine scanning, residue identification like reactive residue identifications, or protein engineering options, or building a crosslink between protein from ab initio methods. As I already showed, protein reliability report. Then if you are dealing with non-standard amino acid residue, that also you can take care of. If you want to see multiple amino acid residue, multiple sequences of different protein, that also you can see in sequence viewer. Then protein titration curves. So basically all things which are related to protein, DNA, RNA, antigen, antibodies, those kind of biomolecules. So all things are already present in the bioilluminate suite. So with this, you will have all options available with you. Not only to that, here is also one of the list of all those options which you can do. So basically, as far as my knowledge, you can do all possible things with your biomolecules. You can just think of something and it is there. So don't hesitate to think something which is random. And I'm sure Schrodinger will have answer for it, or module already available for it. So other than that, like there are many other subsuits present in the Schrodinger suite. So far we have only looked for the biologic suite, which is mostly dealing with the biomolecules. But there is a PyMol for visualizer, which is fastest kind of visualizer. Then if you are doing small molecule drug discovery, so we have for that we have various softwares available like docking, pharmacophore, QSARs, other thing. Even if you are dealing with materials like nanotubes, nanoparticles, so that also can be studied, or polymers or membranes that can be studied using material science suite. Or if you want to analyze chemoinformatic library, that is also considered in discovery informatics. So basically it's a complete solution which we have, and all options are accessible to you. With this, at last, I would like to acknowledge my team who are located in Bangalore, and we are helping you out in all possible ways. So please do not hesitate to contact us for further questions or queries. Additionally, if you like the software, so we also provide a 1 month of free evaluation to the users, and that's free of cost, but you need to have a compatible machine, at least i5 or i7 type of laptop or big machines. And we, along with this free evaluation of software which has all access to all modules, we provide free training. You can always contact us for the training to learn the modules for your queries. But the only condition is you should have this installed on your departmental desktop, so that it is accessible to all of your students and not limited to the particular one. So for that, the best possible way is to register yourself on Schrodinger.com, and once you will have your account, you will have access to all internal videos, tutorials, or software setups or various workflows with you. So other than that, you can also write an email to our business development officer Shelvia. So it's our email ID shelvia@schrodinger.com. And you can, in case of any scientific query, you can contact me on my email ID. With this, I would like to thank you to all of you for joining the session. And with this, I would like to open the session for questions if you have. I'm sure multiple. So these questions I will try to answer best possible way. I think it is. We will see how it is addressed. Otherwise, you can always write me on the email. And finally, I would like to thanks to Dr. Anwar for conducting such a session, and I hope it will be useful for you. So thank you very much again, and
Okay.
Dr. Anwar, if there are
Thank
few
you. Thank you
questions.
very much, Dr. Prajwal. And I would like to add that it was a very amazing webinar as compared to all the previous webinars we had. Very interactive. He started with the basics, and each and everything he covered up to the mark. So there is a request from one of the delegate, Hitesh Shahare, Dr. Hitesh Shahare. Dear sir, request to arrange a similar kind of webinar for the demo of molecular dynamics and simulation study. So how the people are interested in this type of the activities in Scott NGR? We conducted our first webinar on this molecular docking. Dr. Pritesh was there and impressed with all the tools available with the Scottinger. Most of the principal and HODs they requested me to have a session on homology modeling. And now there is a number of the people are requesting for the demo on molecular dynamics and simulation. We will definitely talk with R. Raghu sir, and I hope that he will definitely agree to the next webinar also. So I'm very much thankful to Dr. R. Raghu sir also, along with Dr. Prajwal. So coming to the this session, this question answer session, I will just read the questions which has been asked. So from where the Rahul Sachidev, the question is displayed on the screen. From where the ligand came in the structure that we built. This question
So
is on the screen also.
yeah, so the thing is, from where ligand comes into picture. So it was, first of all, it was already present in the template structure, means the crystal structure. And then while building our model, we chose this option. I wanted to incorporate a ligand in it. If you remember that panel, which if you want, I can show it again. So for example, in homology modeling panel, can you see this particular option which is present that include ligand and cofactor? So I selected this particular option, so that's why it is in the homology model. So it is straight coming from the crystal structure.
Yeah. Uh, the next question that is displayed on the screen, that is Renu Shehrawat. Sir, if two or three chains available in the selected protein structure, should we have to remove extra chain in protein preparation? That is on the screen. The same question is displayed.
Uh,
Can you see the
uh,
screen, sir? The question is also there.
no, I cannot see the screen. I think.
Okay, I will read it.
Yeah, I got the thing. So, if two or three chains available in the selected protein structure, should we have to remove extra chain in protein preparation step before docking? So that the answer is, uh, if you ask me this question, I will look into the bioactive, whether it is biologically active. So, for example, there is a protein which exists in dimer form. So, if you have such an example, that the bioactive form of your protein is the dimer. So in that case, you need to retain both chains. If it is just a unit structure coming from crystallography, then you can simply remove those other chains. But again, before that, you need to be sure about one thing, and that thing is whether your ligand binding site is present in single chain or it is present at the interface of multiple chain. That you need to see, and based on that, you need to decide whether to keep other chains or remove other chains.
There is a question from Renu Madam. What are the criteria of the PDB ID selection, or how to select the best PDB ID other than low resolution criteria?
So other than low resolution criteria means, as I have already explained, there are multiple parameters. For example, resolution is also one of the. Other than that, whether ligand is present in it, how much is the sequence identity, how much is the sequence similarity, whether there are missing residues present in the crystal structure or not. So regarding ligand, whether it is present or not, and other than that, what is the biological activity of this ligand. So these are the various parameters which you need to consider before choosing a
Pooja
course.
Gatki, there is say asking how you can purchase the Mesto software. So, sir will be displaying the last slide again. You are having their business development person, Miss Shelvia is there. Her email ID and mobile number is displayed there. So definitely they will be helping you how to purchase this software. And some of the people are asking that how to get the free version. Free version means 1 month free trial is available, and that should be at academic your college PC, institutional
Yes.
PC. So definitely you can mail through your college ID through a proper channel, and they will provide you the license as well as 1 month free trial. Also, they also provide the training. Not up to the providing this license, they provide the training also if you are really interested in this software. But the thing is that expectation is that you should properly use it and you should produce publication in 1 month. Can we publish research? Yeah, and the next question is, can we publish the research work by using Schrodinger software if we don't have a license for this software?
Okay, so first of all, like from our side, there is no foundation on you, like you should publish or not. But the thing is, if you publish, that is all beneficial to you. We don't stop you for publishing your research. From our side, like we always encourage you to publish result, to perform your project in the period of 1 month. Try to finish it. That's what is encouraged. You can always interact with us hundreds of times. We can have sessions, and we can basically we can plan and design your projects and try to get it finished as well as published soon within that particular time span. But again, it's not a one side affair, it's a two side. You also need to involve, you also need to give your 200% to accomplish your result. We are always there to help you out.
And one
So
thing
yeah,
I would like to add that if you are publishing the research work using this Codanger software, you have to mention the name of the software there properly in your publication, and which module you are using. You have to properly mention it in your publication.
yes, yeah,
So, and there should be the acknowledgement to the Codanger also at the end of your publication. So, these
that
are
is
the
better.
some of the question. As we are just reached to the end of the session at uh,
Okay,
now it
so
is
if we are reaching to the end, so one thing which I would like to always mention s- about the free evaluation of software is from our side we provide you a free evaluation of software, but that doesn't mean it comes free. It as such will cost few lakhs, and that much lakhs we are just providing it to you for free to promote science. So one should always consider to use it as much as possible. They should not waste even single minute of this evaluation period of 1 month. So that's the only
exactly.
suggestion from our side. Please consider it genuinely that this is for the help of science, and one should not waste or take it granted that I have got a free evaluation of software and I could misuse it or I could not use it. So that should
Yeah.
not be the case. You should use it in all possible ways. All modules are available, and every time consider that this software costs lakhs of rupees, which you are getting it for free.
Yeah, yeah, definitely, very correct, Prajwal, because it is a very costly software. It is in lakhs, and they are giving you full version, totally full version for 1 month. You have to just learn from that those who has not used them, and they are hunting for this software. So now the time is with you. You have to utilize it as maximum as possible. And now it is a lockdown period. Totally, you are free at home. 24 hours you are totally free. So utilize your time properly. So we come to the conclusion. Now the announcement is that on the next Sunday we are having a virtual lab. So we came to the solution of conducting the online lectures. More than 90% of the colleges and schools are using online tools, Zoom, WebEx, and all the other tools, Google Meet, to conduct the theory sessions. But there is still a great question mark: how to conduct practicals? Okay, so we have a great session, great speaker also for our next session. That is on 2nd of the August. How can you can design your lab virtually by using these online tools. So you should not stop at this moment conducting the practical. You can still continue the practicals. So attend this next session. It is not only useful for the teachers, it is useful for the students also, because they will be also getting a learning how the teacher will be explaining those tools and how they should be ready prepared. So attend this session. The registration link is the short link is given on the screen. So using this link register, you will get the details how to register in the next Sunday. 11 o'clock will be live. Again, I'm very much thankful to the Scott engineer, especially Dr. R. Raghu sir. On a single request, he agreed for this session. And not but most but last not least is Dr. Prajwal. Apart from his busy schedule, now today is Sunday. All the week they are totally busy in conducting sessions, they can training and all. And today is Sunday, is only one day they are getting relief. So still they are live with us. Half day has gone now. It is near about 12:30, and he since morning he is with me. Not in the morning, last evening he is with me for this all setting. So I'm very much thankful, and all the best to you, Prajwal, for your bright future in this Squad Ranger journey. So thank you, Ajay, all the delegates from different states. You are live to this session, and I hope that in the next session you will be also there and spread this registration link as maximum as possible. So hope you will be using this tool, contacting Scodanger. If you are not written the email ID, just go to the Scodanger website. You will be getting all the contact details there also. Or if not, again you can contact me. I will provide you their details. So many ways are there to contact them and to use these tools. So with this message, I'm just closing the session. Thank you very much. Shall I close the session, Pavel?
Yes, please. Thank you
Okay,
very
thank
much.
you. Have a nice time.
Yeah, you too.